Let's make this a more interactive presentation. Can you all hear me? Am I audible?
Yeah, yeah, we can
Okay.
hear
If
you.
at any point in time you can't hear, if there's an issue, let me know.
Sure,
And I will
sure.
certainly see what best can be done because you never know these systems. Okay, again, a very good morning to all of you. And thanks, Dr. Rohit Kumar, for that very kind invitation. It's been a very hectic time for us here because end of the year, there's too much of planning for the next year. But I normally don't say no to technical talks because that's the only way, we learn a lot. It's both ways. So what I'll do is I'll try to make this very interactive, right? And so if at any point in time you have questions, you can raise your hands or enter your questions at the chat window. I will certainly try to stop every half an hour, okay, for you to ask questions. But in any case, at the end, as I'm mentioning, we'll have a brainstorming session. We'll make it very interactive. Last 15 minutes, right? So after about 1 hour, an hour 45 minutes, we'll have a very interactive session, okay, where you can ask any question that you may have, not only in the topic that I'm talking today, but generally in the overall area, which is a very wide area, right? So what I'll do is I'm going to switch off the camera just because it'll conserve the bandwidth and I'll come straight to the slides. If you just give me a moment, please. Okay. I presume my slides are visible to all of you.
Yeah, sure, sure.
Okay. Okay. So let's start. And again, looking forward to this, discussion or talk today. So I'm going to talk about a very interesting, area which is becoming very, very important in the last 5 years. I would say 5, 6 years, particularly in the last few years, has become one of the dominant areas now in computer science and electrical engineering. And many of us are working in this field, right? I'll give you some detail later on. I am, as Dr. Rohit Kumar mentioned, I'm in the University of Queensland, IIT Delhi Academy of Research. And I also serve in the computer science department in IIT Delhi, also in the University of Queensland, Australia. I actually wear many hats, run conferences, editorialships of journals, and tons of other things. So it keeps me busy around the clock, 7 days a week, with not much break, really. So today we look at really the very cutting edge area of the intersection of machine learning and edge computing. Actually, a broader topic would have been machine learning and systems engineering or systems. Edge is one of the systems that you, as you well know. So let me talk through the details of what my plans are today. But before I come to that, a very quick peek at the University of Queensland IIT Delhi Academy of Research that I am heading. UKIDAR started 2.5 years ago. This is one of the very important collaborations between India and Australia, specifically between IIT Delhi and the University of Queensland in Brisbane. For those who may not know, as of course, IIT Delhi is known, and all of us know it's an institution of eminence in this part of the world, but Queensland is ranked top 47 in the world. They are the top university in Australia with a strength of about 50,000. Unbelievable, right? 50,000 students, about 5,000 plus faculty and staff. One of the largest universities and the most prestigious universities in Australia. And we work in every area, right? So the Academy of Research, spans across all the areas, all sectors, whether it's energy or environment or biotechnology or bioinformatics or computer science, electrical engineering. So we really work with all the departments across both the universities. And in this collaboration, one of the key areas under the computer science umbrella is, of course, the systems research. And in it, we have machine learning and AI and deep learning. And my talk today will primarily specifically cover that. And at the end of the talk, as I will mention in my last few slides, we're very open for any collaborations. A lot of good things happen because one collaborates. And I will elaborate more of that later on. So let me start by sharing with you what's the agenda today. What is the agenda, right? So much for the introduction of UKIDAR. If you need any details of UKIDAR, you can go to the ukidar.org page and get all the details. And a lot of people who want to do a PhD and get a joint PhD degree between IIT Delhi and UQ, this is a great place to come. We only offer PhD programs. There are no undergrads and masters here. So it's a very prestigious cutting-edge academy of research, where a student also has an opportunity to spend 1 year in Australia and 3 years in IIT Delhi. So it's a 4-year PhD program. Coming to the agenda of my talk, I'll start with the motivation and the introduction and what are the problems that we're talking about. I think the systems perspective is getting to be more and more important, as will be evident in the next 5 or 10 minutes. We need to, one of the weaknesses in our ecosystem is systems perspective. Okay. We seldom, a lot of us do theory or simulations, and we seldom remember that, it is very important to dirty our hands on building something. That's also what we inculcate to all our students in UKDAR, that look, try to build something. It could be a simple POC, it could be a simple prototype, right? But try to have something, some system which you can build and showcase to others, right? Within that systems perspective, right, you will figure out that it's turning out that the edge intelligence systems is a new word that has been coined of late in the last few years. And these systems are becoming very, very important, the edge intelligence systems. Specifically, systems such as, the AI, ML, deep learning systems, and I'll tell you what the difference is. Federated learning is becoming very, very important area. And of course, the union of these two is becoming very critical. There are many more areas that I envisage are going to emerge in course of time, right? What I will do is at the end of half an hour, right, after about half an hour from now, once the introduction is done, I will give you, we'll do a deep dive, because, at the end of the day, every talk, it's good to, showcase the work that I am doing with some of my very, very bright students. And I'm happy to share with you that DTU that I collaborate with very often, Delhi Technological University, I do have a very strong collaboration with many of you and many of the students. And that is, yield some great, work, including some excellent publications. But I do guide a large number of students at DTU, in addition to the students at IIT Delhi and other places. Specifically, if you look at the recent areas that we have worked on in the intersection of machine learning and edge computing, you see that there are three specific areas that I'll talk about today. And this will take most of the time because I really like to go deeper into these areas. And the areas are the performance of deep neural networks on resource-constrained edge devices. So what happens when you run these very complex, systems, very complex models, call them models, right? Such as DNNs, it could be CNNs, it could be reinforced learning systems on resource-constrained edge devices. What is the performance? So we'll go deep and look at what the performance issues are and try to get a better understanding. So some very recent results which have not even yet been, in fact, the paper is going to be presented in a few weeks from now. I'll come to that. And then we look at how do these systems, what happens when you run these complicated, models on devices such as, which are becoming pervasive, mobile devices. They're pervasive, they're all around us. Crowdsourcing is done thanks to these mobile devices, right? And as we all know that these are the devices, the mobile devices, that are becoming smarter and, smarter with each passing day. So we look at specifically what happens when you run these on mobile devices. Clearly, in addition to sharing with you many results, I'll share with you a lot of challenges and open research problems so that many of you could, begin to work on this area or extend the work, our work and other work in the literature. And finally, in the last maybe 20, 25 minutes, we look at a very important concept called federated learning and see how we apply this at the edge node. Very interesting initial results that we've got in trying to leverage federated learning at the edge nodes, and some lessons learned, and how do we extend this work, right? How do we stretch it forward, and so future research directions. And finally, of course, last but not the least, I'll spend good time in challenges and future research directions, and conclude my talk with some interesting takeaways, and of course, open the floor to question and answer. So I hope this is clear to all. I hope my
Yeah, sure, sir.
okay, so that's the plan, and let me now quickly start. Let me again. I'm going to make sure that. All right, so let's go ahead. Okay, let's move immediately to acknowledgements. I'm very happy to share the names of my collaborators. Delighted to work with many, many students. I've named a few here only because these are my co-authors, but there are many more from both IIT Delhi and DTU. Specific mention of Tanmay Jain, Avnish, Ishan Prakash, Anirudh Bansal, all are in DTU, I think in computer science department. They are, I think, fourth year undergrad. Some of them are third year undergrad, but very, very sharp in machine learning and AI. It's been a pleasure working with all these students, including our students in the computer science department at IIT Delhi, Manupriya Gupta, Pavas Goyal. I do collaborate with many, folks across the globe. One of them is Rohit Verma, who's at the University of Cambridge. He finished his PhD from IIT Kharagpur and now in Cambridge. I think he should be joining any IIT in the near future as a faculty. And my collaborator in IIT Delhi is Professor Huzur Saran, Professor Shrikanta Vedatur, both in the computer science department. Shrikanta, we just begun, but with Professor Saran, I've been collaborating for almost 2 decades now, ever since we joined this place. So again, great collaboration, which I think in today's times is very critical in doing anything, whether it's a startup or faculty or a student or even in your own, organization. So again, with those acknowledgements, and as I said, I've not listed all the students here because many of them, with them, work is in progress. For example, with DTU, we also have students in IoT and 5G. They're doing some interesting work yet to be published. These are the students with whom we have published work, and the publications have been accepted in very prestigious forums. Okay, so but there are many more, both from IIT Delhi and DTU, that are working with me. About 10 additional students that I've not listed over here from both the institutions. If you look at the startup ecosystem today, and I thought I'll start with this, right? So, it is very important to realize that with each passing month, I mean, I think quarter is too long a time. With each passing month, we are seeing a huge growth in the startup ecosystem. And why am I showing this slide? I'm showing this slide because the interest is phenomenal. If you look at the landscape of the AI ML startups on the left, you'll be amazed. I mean, I didn't even know this, right from speech to machine learning applications to computer vision applications, right, to smart robotics, or look at visual personal assistants or NLP, speech recognition. That's becoming a very hot area of late, thanks to the reinforced learning, right, and other deep learning models. Gesture control. I know that there's a lot of work going on in industrial IoT, which leverages AI and ML. But unbelievable, right? Look at the space. It's exploding, the startup space. And if you look at the right side, you'll find there's a deep learning startup. Right? There's so many of them. Every large company, including Amazon, obviously is working on this area. But good to see mushrooming startups in the area. The lesson from all of us is that we can do it if we want to. We can have our own venture, a startup within our organization, right? It's just I think strong collaborations. That's exactly what we try to do in UKIDAR, foster very strong collaboration with industry across the globe, Australia, India, anywhere in the globe. And we try to ensure that that collaboration leads to some solid output, solid outcomes, which can then be showcased all over the globe, right? So I repeat that collaborations are very critical in the area that we are talking today, right? Let's go ahead and talk about systems, right? So this is an interesting slide. I mean, so what I'm talking about today is going to be really the whole space of the intersection of machine learning or deep learning with systems. But the systems word is a very wide word, right? You may ask me a question that, look, what exactly do you mean by systems? And my answer there will be that, look, yes, it's a very wide word. It includes computing systems. It includes communication systems. It includes operating systems, right? So systems is a very wide word. This slide tells us how we are, look at the evolution in, let's take an example. And let's take an example of a communication system. I'll come to other systems later on, right? But let's take a look at the peek at the communication system, right? You see how we are evolving. I'm not going to go through every line over here, but observe that from very traditional aspects of systems, right? Traditional means, you had well-defined boundaries, right? Like the OSI, ISO 7-layer model, very well-defined boundaries, right? That was true even in computer systems, right? I mean, OS was very well-defined. The various tasks were very well-defined. And then in the last 10 years, we moved on. I remember IBM was the company where I had spent good 7-8 years, and they spearheaded a software-defined paradigm. So a lot of interesting work then went on to, as we call it, software-defined paradigm, which includes software-defined network, software-defined security, everything software-defined, because it is easier to manipulate this, the system become very flexible, right? If everything is hardwired, it's expensive, number one. Number two, it's inflexible, right? So the software-defined paradigm was a game changer in the communications and the computing industry. And if you look at the current networks now, I mean, and the ones that we are talking about today, these are very complex networks, right? For example, IoT, edge, which is my next slide, cloud, right? And that they in turn are many categories of these networks. And we know the advent of 5G. Now we talk about 6G networks, right? But what are 6G networks? So if you go deeper, you realize that 6G networks are exactly those networks which are, they're 5G networks, but throw in AI, ML, DL, and we'll come to what the difference is. Throw in machine learning, and that is a 6G network. So, intelligent networks of the future that are driven by cognition, and I'll come to what cognitive systems are, those are really under the umbrella of 6G networks, okay? So how systems are evolving has been a very interesting journey. Today, no one talks about ISO SI 7 layer model because the layers are fuzzy, though there are boundaries, but they're not very rigid, right? It's a very, very complicated world. And that complicated world is a world of systems, where on the one hand, if you look at the rightmost side, you see that you have those tiny devices. We used to earlier call them sensors and actuators. I remember our first few publications were in sensors and actuators. Uh, and then that evolved into what we call IoT devices, right? So the rightmost side is what you will see in the figure is IoT, the whole world of IoT. And then on the leftmost is the large world of servers. This includes cloud servers, it includes your data centers, right? So for example, all our mails in Google or Hotmail, all the mail systems, social media content, they all rest on these servers or data centers, right? All across the globe, huge servers, huge data centers. And in between, you have the advent of edge systems. Okay, now that is a very important development that happened about. So, who started research, edge computing, or call it edge nodes, or let's call it edge computing? If you go back in time, one of the giants in the area, Cisco, and I would do work closely with Cisco. It's a great pleasure to work with Cisco, one of the giants in networking. They are the ones who defined an area called fog computing. So I am would like you to encourage you to look at the internet and search on fog computing. That word came from Cisco, and what Cisco said was, "Look, cloud is too far, right? Cloud could be really far from the IoT devices." And that means the implications are that the latencies are very high, right? That is not acceptable for real-time applications such as autonomous driving or vehicular networks, or let's say some other cutting-edge real-time system like industrial IoT. We cannot afford such latencies, right? Also, the bandwidth between IoT and cloud could be an issue. So let's have a layer in between called the fog, but now it's evolved to the edge now. So that layer is a layer of edge systems or edge computing, which is in between IoT and cloud, right? And the advantage of this is very clear that your latencies are going to be much lower because edge is closer to the IoT devices, right? The edge systems are much closer to IoT, so latencies are much lower. Therefore, the performance is better. The only thing is, edge has a limited resource. Edge is resource constrained. It doesn't have a large power or large memory or large computational power. So you only have that much in the edge. I mean, a mobile phone could be an edge, for example, a laptop could be an edge. So it doesn't have humongous resources, unlike a cloud or a data center. And so you have to do with whatever best you have, right? And that's the challenge which I'll talk about in a short while from now. So edge is in between IoT cloud. Cisco used to call it fog. If somebody asks a question, which is asked many times in our conferences or in our meetings, what's the difference between fog and edge? The difference is there. There is a subtle difference, but for the purpose of this talk, we can use the word edge and fog interchangeably. Essentially, there's not much difference. Okay, it's a very subtle difference that I'll come to later on in the talk. Okay, so we are seeing tremendous strides, progress in systems, and we're seeing major diversity from tiny IoT to edge to huge whale systems, which are the cloud systems or the data centers. So the diversity is, so observe what's the takeaway from this slide. There's plenty of diversity. These are heterogeneous systems, and they're evolving from one end to the other end. Okay, the edge nodes. So again, first question, what are the edge nodes? And I think that is all answered now in my last slide. And by the way, I'm going to go deeper and deeper. So just bear with me for all faculty members. And I know that many of you are doing some great work in the area. But bear with me. I will need to introduce the concepts, and then I will immediately go into the details. Okay. So I need to another 10 minutes to come to more details because I have to set the tone for the talk. And I hope that's fine with all of you. So I think the question of why the edge nodes is very clear. I'm going to do a mic check every now and then. I hope I'm audible. If you could just
Yeah, sure, sir.
okay,
Yeah,
great. Yeah, it's always good to do a mic
yeah,
check
sure. Yes, sir.
just in case something goes wrong. So why do we need edge node? I think that answer should be very clear because if you don't have, so let's answer the question. Let's answer the reverse of the question. If you don't have the edge nodes, then everything, all the data from the devices, the IoT devices, is going to land up in the cloud, okay, or the data centers, and that's far away, right? Could be tens of thousands of miles away. It could be thousand miles away, right? It could be hundreds and hundreds of kilometers away. And so you don't want to take a chance with that because that will not be acceptable to real time or semi real time application. So therefore, you have the edge nodes over here. Why edge nodes? Because number one, you want to minimize the latency. Number two, you want to maximize the performance. You want to maximize the hit ratio. You want to make the systems more intelligent, and you want the intelligence to come closer and closer to the IoT node. IoT node, by the way, are the end devices. So all your sensors, actuators, drones is IoT, UAV is IoT. Cell phone can serve as both IoT as well as edge devices. Okay. In fact, the way cell phones are evolving, it is not a surprise that they're getting smarter with each passing day, so they can now qualify as edge nodes, right? In addition to your laptop and simple mini servers. So I think it should be clear why we need edge nodes and why, therefore, the research on edge computing is becoming extremely critical. But the research is a challenge because number one, these are very heterogeneous nodes. Number two, cybersecurity is becoming critical, right? And I'll talk more about that later on. So security is very critical, privacy is very crucial. You want high performance and all those all that jazz, you want. And so you got to do a lot of research to ensure all these properties are uh, adhered to. And then as you move from systems, and let me kind of change the gear for just a short while, and that is machine learning. Look, the machine learning space is expanding, or with each passing, it's taking, the growth is unbelievable, incredible. But there's a lot of confusion about this area, and I want to just highlight this to the audience that look, AI is the largest of the circles. So AI is everything, right? AI is a very large subset. So a lot of the students over here also, PhD students, when they say AI, we tell them, look, be specific. What do you mean by AI? And then they say, no, we work on machine learning. All right. Well, machine learning itself is a very broad terminology, right? Inside machine learning, you have unsupervised learning, you have supervised learning, and then, of course, you have this new paradigm of reinforcement learning, right? The temporal models. And then you have deep learning, right? So you have this deep learning, which is really a proper subset of AI and a proper subset of machine learning. And here lies these systems or concepts or models, which are the deep learning models. Okay, so they're right in the center. By center, I mean they're proper subsets, and these models are very specific. I mean, you can't apply them everywhere. You have to be careful where you apply them, and we'll figure out where do you apply them and where do they yield some great dividends. But the family, so I like this figure because the family of models in AI ML are fairly large. And there is no clear, I mean, a lot of people say, what do I do? Which supervised learning model do I apply in my problem? Or which unsupervised learning do I apply? Or which deep learning do I apply? And sometimes the answers are clear. For example, if it's video or audio, if it's a streaming video or images, then, of course, I look at deep learning for applications such as classification or segmentation or so on and so forth, right? But there are many systems which have labeled data, and for those labeled data, I can apply supervised learning, right? If the data is not labeled right, then I probably will use unsupervised learning. But the challenge is, which one do I use? That answer is not obvious. It comes with tremendous experience. It comes with expertise. It comes with the kind of application that you're talking about. Okay, so this picture is an interesting picture. And if you go deeper now, and I just mentioned this few short while ago, that if you look at now further classification of ML algorithms, you'll find that there are so many categories of supervised learning. And by the way, these are shallow learning algorithms. Why shallow? Because they really are not characterized by a large number of layers, unlike our deep learning algos, right? Huge number of layers, right? And amongst these supervised, again, you have so many choices, right? You have this right from the simple naive Bayesian to logistic regression to SVMs to random forest, and the list goes on and on and on to care nearest neighbor, which we have been seeing from day one, right? Or if you now look at the unsupervised shallow learning, it's clustering, it's association. And then finally, you have this category of deep learning, which could be again supervised deep learning or unsupervised deep learning. So, which one do you want to apply? No obvious answer. The answer is that you really want to. The answer has two parts. What is my application? Is it dominated by images and videos? Number one. Number two, is it a labeled data? What kind of data is this? Is it labeled, unlabeled? Number three, is the data, does it have many gaps? Do I have a complete data, or the data is very, very partial? It has many gaps, in which case I have to fill that gap, right? That's probably the first step. So no clear-cut answer as to what model I'll apply in what context. It depends upon the context. And now we look at, so with this primer, we will see that this intersection of AI ML with systems becomes very interesting propositions, which means if we go back to this figure now, I like to apply AI ML at the edge. I certainly like to apply AML at the cloud, right? Which can be, because cloud has enough memory and enough processing power. If you look at the IoT devices, the question is, can I apply AI, ML, or deep learning in IoT devices? The answer is probably no, right? Because these are very lightweight systems. So probably no, but you never know what's going to happen in the future. I'm sure we'll have come out with some very smart students at undergrad, master's, and PhD level who will enable machine learning algos on IoT devices under certain conditions. I'm sure that will happen in the course of time. But right now, yes, we are learning them on gateways. We are running AI ML algos on gateways, on edge devices, such as gateways or routers or aggregators also. Okay. And then you find as you go ahead now, so remember, when I said systems, I meant these systems, right? Cloud, edge, IoT, but systems are so many. You have cybersecurity as a system, right? And you can see that today there's a huge plethora of research in applying AI ML algorithms in cybersecurity. And cybersecurity, again, is a very wide area, right? Many of our students are working on this area, which includes intrusion detection, include malware analysis, includes spam and phishing detection. If you go deeper, if you go deeper now in cybersecurity. And why am I mentioning this? I'm mentioning this because cybersecurity is another category of systems. And these are systems which need cybersecurity, end-to-end systems. And so that's a characteristics which is very critical. And in these systems, to infer certain, a category of attacks, or for example, intrusion detection systems, or to prevent intrusion prevention systems, you are probably seeing a lot of, AI, ML, and DL being applied now, depending upon the data, depending upon the context. Uh, the areas are all the way from spam mitigation to malware detection to denial of service attacks, distributed denial of service attacks, user identification, theft, identity theft. Social network security is becoming a very important area, right? All these networks, the graphs that so you can extract a graph from the social networks, whether it's Facebook, LinkedIn, or whatever, Twitter, and then you can extract some great feature of the graph and answer many questions. But a lot of these systems are subject to cybersecurity threats. Okay, so in summary, all kinds of systems, not only computing, communication, but even cybersecurity systems, where you will find that we are now applying both shallow learning and deep learning in cybersecurity. You can see this is a very interesting slide, which tells you all kinds of papers that have applied supervised learning and unsupervised learning in cybersecurity. And an interesting observation from this slide is that there is no one that fits all, right? There is no one algorithm or mechanism or model that fits all. You'll have to experiment, right? Even in intrusion detection, there may be many different categories of data, and so you'll have different models. Malware analysis is different, spam detection is different, right? And in unsupervised learning, which is characterized by clustering or association, you'll find that they're totally different category of algorithms. So in summary, the intersection of AI, ML, and systems is a very, very important area. And not only do we talk about the importance of the area, but we realized this a year ago. And many of us, I including my colleagues, who many of you may know, started this new conference in India, which turned out to be a very very important conference. In fact, I know Dr. Divya Shikha Setia, who's probably in the audience, and her students had a paper in this conference, and so kudos to the team that had papers here. It was one of the first. So it was the first conference in AIML system which started this year in Bangalore. Just ended 2 months ago, and it was an initiative of ComsNet Association, that is the board that runs the famous ComsNet conference, starting in about 15 days. Strongly supported by ACM, SIG AI, SIG Mod, SIG KDD, supported by Government of India, and of course, as you all know, ComNet is one of the very very prestigious conferences supported by all the IITs, triple ITs, uh, NITs, multinationals, and I think we'll probably have DTU's logo also there in course of time. So the area became so important that we started this international conference only focusing on the intersection of AI, ML, and systems. And by these two, we mean both systems and AI, ML for systems and systems for AI, ML. Okay, so I repeat, this includes machine learning applied to systems, right? For example, applied to edge, applied to IoT, applied to cloud, applied to cybersecurity, right? But it also includes systems for AI ML. Do I need a new simulator? Do I need a new simulator in AI ML, which is a digital twin? Do I need a new processor, right? Let's say NVIDIA processor for AI ML. Do I need a new dedicated FPGA, a new chip? So it's both ways, AI/ML for system and system for AI/ML. Okay, so that tells you that how critical this area is, and is going to remain so for a long, long time to come. Okay, so with that, I'm going to stop my part one of the talk, and I will go now immediately go deeper and see some interesting results and areas of research going forward. Okay, any questions till now before I move on?
Yeah. Any questions from the participants? Just most welcome.
Are there any? I'm not seeing.
Okay. Maybe they can have the questions
Okay,
later on.
we
So
can look at that later on. So
sure,
go
sure,
ahead. Yeah,
sure.
probably it's not the right time to answer. Okay, so let's move on, and let me skip that right now. So what we are doing is, I remind you all that we're looking at the intersection of machine learning and on the edge devices, right? That is with edge computing. And but before I come to this slide, a quick recall that one of the most complicated deep neural networks, one of the complicated family of deep neural networks is convolutional neural networks, as you all know. These are characterized by, so there are two important observations that I want to highlight with colleagues in this talk today. One is that there are two things we use as far as the DNNs is concerned. One is the width, other is the depth. Okay, how deep are the CNNs or the DNNs? Because CNNs are all deep neural networks, right? So one of the examples of deep neural network is convolutional neural network. How deep are they? Which means how many layers do they have, right? And how broad they are, right? How broad can they be, right? What are the number of channels, right? So how broad can they be? But depth. So if they have larger and larger number of layers, right? Let's say hundreds of layers, then the processing becomes a nightmare, right? Because every layer, you're spending time in processing, right? Every layer you are updating the weights, you are forwarding it, or you're back propagating it, depends upon the model, right? So by the time you reach the end, the output, right? Output could be, you can classify an image, or you could do a segmentation or whatever, right? You want to highlight a specific aspect of an image or a video, or or regions. That's the end output. But to arrive at that output with high accuracy, I repeat, with a high accuracy, right, as compared to the original image, is a lot of work. It takes a lot of time. It takes a lot of effort. When I mean effort, I mean computational effort, right? So just recall that computational neural network, which are a specific family of deep neural networks, have an input layer. They have all kind of layers in between, and these are called the hidden layers, right? So for example, your convolutional layer or pooling layers, right? So simple example is your convolution layer followed by pooling layer. Then you can have these pairs repeated many times. So conv pool, so on and so forth. These are all hidden layers. You can have ReLU activation layers finally, and that leads to the overall output layer. So how many layers depends upon the CNN. I mean, there are tons of models now, right? You'll see many of them in my talk. In any case, there are many models. How are they different? They're different because their structure could be different. Number one, number two, number of layers are going to be different from one CNN model to another CNN model. Number three, some may have a large convolutional max pooling pair, some may have small. So all kinds of nuances and complexities are thrown in, and why did it happen? Because as CNN research advanced, they realized that I could, faculty members from all over the globe or industries, R&D lab realized that maybe they could improve the performance by adding one more layer. Maybe they could further, improvise on the weights by doing something more intelligent. So that's how we have so many CNN models. There's really no one model that we need to study, right? So as you now go forward, you'll find that deep learning running these models, which are complicated, as you can see on the bottom right side, on the edge is extremely challenging. And the reasons are many, and you know the reasons by now. One is that the models are highly computation intensive, okay, because every layer is work. And by work, I mean memory consumption, computational power, and energy expended, energy consumed. Please keep in mind that what are the important metrics, and I will come to that work that we have done, very interesting work in about 10, 15 minutes. That energy is a metric that that cannot be ignored, particularly in devices which are very limited battery or power or energy. For example, mobile phones, right? You cannot ignore. You may ignore energy in legacy edge systems, but not in the small form factor mobile devices because energy is critical there. Good to know what is causing the energy burnout over there. Okay, so we'll look at that. Uh, as I mentioned earlier, the area is growing wider, which means more filters within a layer, and it's going deeper, more and more layers with billions of parameters and millions of floating point operations, right? Uh, Tons and tons of weights that you need to refine with each passing layer. And finally, when you converge, you realize that these are very high accuracy. Accuracy becomes an important metric. Deeper models provide high accuracy. Now, as I go deeper and deeper, as I include more and more layers, I am probably going to provide high accuracy, but there's a cost, and the cost is computational complexity. So please understand that there's nothing which is perfect. Every time I talk to our students, right, whether they are PhD students or whether they are masters or undergrad students, I tell them, look, let's explore trade-offs. All of us are engineers, right, or scientists, right, scientists and engineers. And it is very critical to explore trade-offs. There's nothing which is perfect. Someone says, I have a system which is best till now. Well, I will take it with a pinch of salt. I'll probably blacklist that person because that statement is going to be completely false, right? There is nothing perfect. It's probably good in comparison to other systems, but it's not doing well in some other metrics. So the trade-offs are something that we have to examine. And one trade-off is between accuracy and computational complexity, okay? And this then leads to computational gap between DNN models and the less capable edge systems. Why are they less capable? Because they're resource constrained, right? And therefore, there are many approaches that are proposed to bridge the computational gap between the complex models that you saw. This is one example of a very complex model and the resource constraint edge system, which you now know exactly why they're resource constrained. Okay. They have a finite processing power P, they have finite memory M, they have finite energy E. They also need to be secured in every sense. And so please understand that and I'll come to the metrics. There are tons of metrics that are important in these systems. In fact, I probably should, yeah. So the metrics, we'll come to those metrics, but one of the important metrics is energy and other is accuracy, but there are many others like latency, throughput, right? And the list goes on and on and on, and we'll look at all those metrics. But remember, the key takeaway of this slide is that there is no perfect model. There is no perfect data. There is no perfect system. Whatever you do, there's a trade-off. It's good to showcase not only your results in the papers that I will do now in about 5 minutes from now, as I take you through tons of our work, but also to understand, it's good to highlight the limitations of the work. What are the limitations? What cannot we, what have we not done? Because that is what you will do then, right? In future, or your students will do, or our students will do. So it's very important to understand these trade-offs. Okay, I hope that's clear to all of you. With that, and now this is the slide that I was talking about where I said I'll come to the metric. This is a very important slide, right? So now the merger of edge computing systems and systems models of machine learning and deep learning and AI, that merger is now called, a lot of interesting papers call them edge intelligent systems. So you're really trying to build intelligence. I actually like the word cognition. You're trying to really add cognition, more and more cognition to the edge systems. And so whether you call them edge intelligence systems or edge cognitive systems, it's one and the same. There's not much difference, okay? For those who may want to know what cognitive systems are, I'll be happy to answer in a short while from now, okay? So the cognitive systems are those that are intelligent, but they're also self-learning, self-healing, and all the properties that are there in the human body, right, which is extremely complex. Now, coming to the metrics that we're going to study, the five metrics here, and they're not the only metrics, by the way, right? So, for example, as I said, accuracy is the key metric in machine learning, which you all know very well. There is latency. Latency means end-to-end delays. Okay. Now, remember, each of the metric can be broken up into multiple parts. I repeat, and I want to probably come. Just give me a moment. I'll probably want to highlight this to come on a video for a moment and highlight this to our colleagues. Every metric can be broken up into multiple metrics, and I'll come to what I mean by that. So don't see these five metrics as the only. These are high-level metrics. We can further break them down, and that's exactly what we do when we write papers, because these are too broad otherwise, right? So let's give an example of what I mean by that. Let's go back to that slide. So here you will see that, let's take an example. Let's take latency. Latency means delays, end-to-end delays. That's a very broad word, right? So latency could be latency at the edge, latency at the cloud. It could be the delays from the edge to the cloud, which are called the transmission delays. It could be delays from the cloud to the edge, right? So already I've broken this into four parts, right? Look at the energy. Energy could be energy of running your model, any model. It could be CNN, it could be reinforced learning. It could be running. So energy component number one, E1 could be energy at the edge. E2, energy at the cloud. E3, energy from the sending data, energy consumed or expended on sending the data from the edge to the cloud and cloud to the edge. Accuracy, security, memory at the cloud, which of course is very large, memory at the edge. Security is very complex because security includes privacy, right? So how do you ensure privacy? Security is a very broad word. Each of you may want to work on one attack vectors, right? As you know, there are plethora of attack vectors, right? So the attack vector in edge is very different from the attack vector in the cloud. Why are they different? Because cloud has much more resources, right? So you have to have even smarter security schemes over there, right? Then you can have security of the communication pipe between edge and the cloud, or vice versa. So each of these need to be dealt into detail. One can dissect them into many components, as we will see in next few slides. And this is a spider diagram. Now, what this diagram tells you is that which one should you focus on? So take, for example, the orange line. The orange pentagon is telling you that for that application, look at the orange, the yellowish orange color, right? The light orange. So this application wants high accuracy, wants very good memory consumption, and wants energy is a very important metric there, right? Latency is not an issue there. So maybe it's a non-real-time application, right? Then there are some applications like the gray one where latency is critical. You want to minimize latency, maybe vehicular network, maybe autonomous driving. You really want to minimize the latency, right? So therefore, latency is very critical, right? Others are not so. Security, theek hai. Accuracy is okay. I can do with 60-70% accuracy, 0.7 accuracy. Energy is important, but not that important. Memory is least of my concern. So where do I... So for every application that you have, healthcare will have one spider chart, right? This is a spider chart, right? Autonomous system will have other spider chart. Maybe intelligent transportation system will have a third spider chart. So each metric is a function of what is the application running on top. And there is no application that will make all these security metrics happy. It's not possible. Okay, it's almost impossible. Well, if you have that, you may probably will have $1 billion startup. So it's going to be your claim to fame. So this is the design space for intelligent system. Have I missed some metrics? Yes, I have. You could include many other metrics here, right? For example, I've not even added fairness, right? Fairness could be a metric. Now, how do you define fairness? We'll come to that, right? There could be some other metrics like, for example, throughput of an application. You could talk about reliability of an application at the edge. You could talk about resilience, fault tolerance. But remember, those are second order metrics. वो बाद में आते हैं, right? They're second order metrics. First order metrics are the one that you see over here. But yes, there are many other metrics. You could define your own metric, by the way. You could have a union of these and others that I spoke about, and maybe arrive at a paper, because it is possible that one of your applications demands that metric, like, for example, very high fault tolerance or reliability, which is not showing up over here. Okay, so the basic metrics are shown over here. The other metrics are the derived metrics. I hope that's clear to all of you. So with that now, let us go ahead and quickly move on to go into details, and let's see some research work in the area. We'll do a deep dive in each of the space from now onward. Okay, so with that, let's change the gears now. Let's see what is this very important area called federated learning, right? Something that many of us are looking at. Many of our students in IIT Delhi are looking at federated learning, right? Now, why am I talking about this? Because this is another area which is in the intersection of machine learning and edge. So obviously the FL algorithm will be running on the edge, right? They could be running on the cloud, certainly, but we are talking about FL algorithm running on the edge. So what is federated learning? It's basically a decentralized machine learning approach, right? So look at the figure on the right side, right? So you have this server, the global server, call it a global server, and look at all these devices. I mean, these, for example, could be edge devices, for example, right? And so it's a decentralized ML approach. So basically, what's happening is I am distributing my machine learning model across all these nodes. Okay, and I'll come to how it's done, right? In a very collaborative manner, these models are learning. They kind of We are improvising on these models. We are enhancing their accuracy or their performance on the edge nodes with passing time, and then I share the updates with the server, which you can see over there. So observe that nodes in the federated learning paradigm, nodes use their local data to cooperatively train a machine learning model required by a federated learning server. One of the key objectives of federated learning and why it started was privacy preserving protocols. You really want to preserve privacy. Let's start with what we mean by that. What we mean by that is I don't want to share my data with the server. Okay, so let's say edge 1, edge 2, edge 3, edge k. So there are k edge nodes, each having its own ML model, right? And therefore the data, model and data. I don't want to share the data with the server, with the master. I don't want to. Why? It'll violate my privacy. Take an example. I mean, this could be a wireless network, right? This could be Wi-Fi. I can have a denial of service attack. This could be Bluetooth. Well, Bluetooth to nahi hoga. It's too limited in bandwidth, but it could be Wi-Fi. It could be 5G. It could be 6G. It could be LTE, right? It could be, a LoRa network, right? So you really don't want to compromise your data. You don't want to send the whole data. Not only because of privacy reasons, but also because you may not have the bandwidth. You don't want to blow your money. So you want to keep the data with you, but just send this the hyper data, the parameters, maybe the weights to the server. Okay, so I'll send the model updates, that is the weights, for example, to the server for aggregation periodically, and then you repeat this step in multiple rounds till you get a desirable accuracy. So you can't keep doing that. I repeat, you will run the models in each of these edge. You will share the weights, or you can call it a metadata, for example. That's called a metadata. You can share the metadata with the server, and then the server will again do computation and then share back with the edges, the model, right? And this iteration will keep on and on, will continuously. So here's a deeper, better figure to explain the general federated learning training process, right? If you look at this figure carefully, you'll see that at the bottom are the participants. This is the edge nodes. Okay, they could be IoT nodes, but really I won't use IoT for federated learning because they're very resource constrained. So I'll probably use edge nodes. Okay, And then on the top, you have the server, which is the owner, the centralized master server, right? So step one is that the server will set to task initialization, will send all these updates to the edges. Step two will be then, as you can see, right, that all these edges will run the model. They won't share any data, by the way. They run it locally, so that they do local model training, and then they send it to the global aggregator, which is the server. The server then aggregates the updated parameters, refines the model, and sends the again send the task initialization. So this goes on and on and on till certain time that you achieve the accuracy for your application, right? Because this question is asked frequently: how long will I do this? Well, remember, again, there's a trade-off, right? So what's the trade-off in this picture in federated learning? Well, if you really want a very high accuracy, well, all the best. The model will have to be running between the, you have to be sharing the metadata between the servers and the clients, and the clients are in this case edge devices. Frequently that consumes power, it consumes energy, it can add to latency at the server, right? So clearly one observation from this, again, like what you saw earlier, was that you really want a very high accuracy in federated learning. Good luck, all the best. You'll have to compromise somewhere. That somewhere will be probably latency and the energy expended at the edge nodes. Okay, so very interesting example. You can compromise some accuracy where you'll have a very low latency and you'll have very low energy expended. So this is the example of a general federated learning training process. I thought I'm going to share that with you. So, what are the advantage of federated learning? I hope the overall concept is clear, because I'll again do a deep dive when I talk about the specific work. So, what are the advantages of federated learning? The big advantage are privacy, right? Let's start with the second metric over here. Okay, why privacy? Because you are not sharing the data, the chunk that you have. You're not sharing that with your server, right? With the centralized server. You're only sharing the metadata, which is the weights or some other metadata. It could be anything else, right? Number two, highly efficient use of network bandwidth, because you're not sending the whole model to the server, right? You're only the metadata. Obviously, you are conserving the network bandwidth, which means your costs will go down. You don't need gigabits per second link between the edge and the cloud. You could do away with even a smaller bandwidth, and that is going to be very cost effective for you when you build the system. Finally, low latency, right? Because you're not sending those huge chunks of gigabytes of files, right, or data. Could be images, could be video clips. You are naturally going to have low latency. So several advantages of the whole paradigm called federated learning. What are the key challenges? The first key challenge is communication costs, right? So you are going to, obviously, there's a lot of to and fro communication between the server and the edge devices, right? So there's going to be a lot of communication costs. Heterogeneity of participating devices. You certainly can't expect all the edge servers will be to be homogeneous, right? And they could be completely heterogeneous, right? For example, you could have multiple labs in DTU cooperating, and therefore your servers are all different. The edges are different at each lab, right? And they could be so heterogeneity implies that your data quality will be very different, computational power will be very different, and of course your willingness to participate is going to be very different. Some nodes may be very happy to participate, but some may say, no, I'm very concerned about my privacy or my resources, I'm not going to participate. So you need to look into all those characteristics, right? So heterogeneity has many flavors and colors. Heterogeneity could be heterogeneity of computational resources, memory, power, data. Primarily it's data, remember that, I'll come to that. And willingness to participate. Okay, and finally, the challenge of privacy in the presence of malicious. Now that's a very hot area of research. What happens when you have malicious servers, edge servers, or of course, look, if you have a master server which is malicious, then let's go home. I mean, nothing will work, right? But I'm assuming that all the nodes in the federated learning environment are good nodes. They're not malicious. But if they get malicious, like if some of the edge node get malicious, then what happens to the privacy preserving protocol, which is federated learning, right? So that's a question that needs to be answered. Papers are now coming out, but we really don't have a complete answer for that question. Okay. So in summary, if you look at this slide carefully, in summary, you will see that there are many advantages of federated learning, but there are many challenges. But we like the challenges. And the reason we like the challenges is that because that challenge will then enable us to publish some very nice publications, right? Arrive at some good patterns of publications. Going ahead, what are the practical issues in federated learning and implementation? Right? Uh, there are several practical issues. There are statistical challenges. Now, what do you mean by statistical challenges? Statistical challenges mean that the data can be very widely varying from one edge node to the other. And I will come to one of our publications where we talk a lot about that. What we are saying is that we have to be very careful as to the distribution of data on the edge nodes in federated learning environment. Okay, let's go deeper. Is the data uniform? Does it have the same distribution? Is the data independent and identically distributed? Many of you have done a course in probability and stochastics have understand the concept of IID, independent, identically distributed data, right? So IID means it's very nice property, right? It's independent. But many times data are dependent. Like you can see this DAG below, right? The three DAGs. So statistical challenges are very critical, and the reason why they're critical is because if some node fails, which has a large amount of data, well, you're in trouble. How will your federated learning algorithm converge? So one has to examine this challenges related to data, and therefore these are the statistical challenges, which mean that what's the distribution, how is it different, what's the mean, what's the variance, what's the moments, what is the distribution, forget the mean and moment, what is the distribution, how will you solve the problem when nodes fail, which means data has gone, right? What's the distribution of data? Is it uniform, is it non-uniform? How do you do load balancing? Is it true, is it the case that some nodes are highly loaded, some are lightly loaded? Because which means that if the highly loaded nodes fail, then you're in trouble. So it's a very interesting investigation area. And then communication costs, right? What are the costs between communicating when the edge communicates with the server, right? This, of course, is also a function of the topology. What is my topology, right? Is it a star topology? By topology, I mean the connection between the edge and the server. Is it star topology? Is it a torus? Is it a mesh topology, right? So that is also going to affect the answers. Resource allocation. How do you allocate the resources, right? I mean, who's loaded heavily, who's not, right? Uh, are you going to give priority to those edge nodes which have a large computational power and large memory, or are you going to give priority to other nodes? So we don't know that. That's entirely resource allocation. Finally, privacy and security. How are you going to ensure security of this entire model, which is right in front of you, right? How will you ensure security? Are you going to encrypt the data? Well, good luck. You're going to waste time. Are you going to have a PKI over here? Well, we don't know. How are you going to ensure that these networks are not only privacy preserving but also secure? Okay, all kind of denial of service attacks. One can have a paper on denial of service attacks in federated learning, and that's a problem that some of our students are looking into as I'm talking to you. Okay. And finally, what are the research directions in federated learning? Okay, what are the areas that we could work on? So, and I'm going to talk in detail about some of these areas because we have some very interesting results in each of the areas. And I'm going to come to results in just about 5 minutes from now. Okay, enough of background and primer. So you can see that the research directions in federated learning start from drop participant. What happens when your edges are dropped? Right? Why will edges drop? Well, edges may be drained out of energy. Number one. Number two, edge could have an attack, a DOS attack, therefore they are gone. Number three, they may have no data. So you really don't need that edge, right? So what is the consequence of, I repeat, and please listen to this very carefully. What are the consequences of my performance of federated learning algorithm when you have dropped participants? Open question, no clear answer. Open research problem. Privacy concerns, I've already spoken about that. Communication security, how will you ensure security of this channel? Asynchronous federated learning. Why should I have everything synchronous? Why can't I have an asynchronous model where I don't worry about that, the real-time updates? I can update non-real time in an asynchronous manner, right? What happens when I have unlabeled data, right? Are there any tools to quantify statistical heterogeneity, right? This is a very important point, and please highlight this in your as you make notes. Are there any tools which can tell me the distribution of data across the edge nodes in a federated learning environment? Because if I can get hold of this tool, I can build such a tool like that with my student. I can tell you you are going to qualify for a SIGCOM or a MOBICOM paper, right? And going to take you to great heights. Okay. Finally, convergence. Everything about federated learning is convergent. When does your if you remember, I showed you this slide, right? That you keep iterating till you converge. Converge means till you reach a certain accuracy, right? So when do I converge? Can I converge faster? Can I have algorithms which are going to give me maybe a faster convergence? So can we work on learning convergence? And finally, what are the applications of federated learning? I think that's very, very important. If you want to work on a prototype in your lab, I mean, for example, our students, even our DTU students, are working on Raspberry Pis or Arduino boards, right? And I must really commend all these students in IIT and DTU who, in spite of the lockdown, have really done wonders at their home or in the lab with these devices. But the question that we have to ask is, what's the application, right? You have to define an application. You can't just say run an app for all the apps. It will not, because one app is going to drive very different metrics, which you saw in the earlier slide, than the other apps. Okay, so there are tremendous research directions in the area of federated learning, such as there are tremendous research similar to what we saw earlier in the tremendous research directions in the area of deep learning, right? So, but it's important to know both, because both deep learning and federated learning are attracting huge attention in the community in the last few years. And with that, I'm going to stop, and I'll be happy to take any questions before I move on now to fairly detailed slides now. You will now see results of our work, some very interesting work. I'm going to present many publications. But are there any questions at this point in time? I'll be very happy to take questions.
Professor, I have a small query that
Yeah,
right now you were talking about the malicious users, right?
yeah,
So my question, since I work usually in reinforcement learning, where we apply it for this cognitive radio users and IoT networks.
yeah.
So how easy it's for you to differentiate between the normal users and these malicious users? Because in my case, like it's not that easy to differentiate. That is why we apply learning that which are the actual malicious users and which are the real users. Right?
Yeah, that's a great question that you asked. In fact, one of my students in IIT Delhi in electrical engineering, along with Professor Arpan Chattopadhyay, we are actually looking at the same problem. You see, the thing is, as I can answer. Let me answer in pieces. First of all, a lot of the work that we do, when we start the work, it assumes that the data is authentic, the users are non-malicious. Okay, because you have to start from there, right? I hope that's clear.
Yeah.
So every time you start, exploring or investigating an area, you certainly want to start with an assumption that everything uh, is good, under control.
Absolutely.
Now you get results, right? So
Yeah.
all what I'm showing you now is under the assumption that everything is hanky dory. There's no problem. Now you complicate the scenario because you have a base set of results, right?
Yes.
You have a
Yes.
base. How do we call it? A base comparison set, which means that there's
Right.
no malicious users or
Hmm.
there's no malicious data. Now you complicate that and see. So the part two is that you now may want to inject the malicious data, or have or maybe launch an attack and enable a good node to become a bad node,
Hmm.
and try to learn from there. So I'm actually doing it explicitly, right? I am
Hmm.
injecting certain erroneous
Users.
right,
Yeah.
yeah, I'm injecting
Absolutely.
them
Okay. Hmm.
explicitly, and I'm trying to get the answers. So
But I
that's
think
what we're learning.
that's like a simulation, right? That we are in it.
Yeah.
But how in actual sense we are going to differentiate between them? So that is my question, right?
No, no. So that's a part three that I was coming to. So that the
Okay.
third part is really trying to intercept the entire traffic at the gateway, whatever the
I
gateway
see.
edge
Okay.
is the gateway, right? And
Mm-hmm.
now to see whether the relevant ML algorithms are going to help you to segregate the data. See, it's a function of what data you have. If it's a
Absolutely.
structured data, then the answer is probably simpler, right?
Yeah.
If
Yeah.
let's take an example. Let's take an example. Let's say I'm getting the IP traffic, the IP layers, right? I'm getting all the headers, right, of
Right.
IPv4, and we know all the headers, right? The
Right.
five tuple that I'm getting. So that's structured data, right? I know the five tuple: IP address, source, destination, port address, source, destination, and the protocol. तो वो तो सारा
Mm-hmm.
structured हो गया आपका. Maybe I
Okay.
know what algorithm to use to figure out what is malicious, what is not. But the problem is when you now have an unstructured data and they're
Mhm.
using unsupervised learning or deep learning, now that's always a challenge, always a challenge. So the answer
Absolutely.
lies in using a couple of algorithms and seeing is one of them able to extract the malicious aspect. That's how we typically
Absolutely.
go about it.
Okay. Right.
You
Right.
may fail, but
Yes.
that's
Yes.
the whole idea of experimenting from
Absolutely.
one to algo to another.
Absolutely. Absolutely. You're right.
But yeah, a very important point that you asked: how do you differentiate normal traffic from malicious traffic?
Because I remember when I had done my first paper in this transaction on mobile computing about this user. So again and again, this reviewer was trying to like stop me on that point only. That actually, yes, you have done the simulation, everything is fine, but yes, how actually you are going to differentiate? Right? So that
Yeah, no, no, absolutely. And also the challenge is more when you have a very slight outlier, right? Let's suppose
absolutely
everything is normal, but I have a small outlier, right?
right, right,
Now it's very hard to differentiate. I think that's a very
absolutely,
tricky territory. But when
absolutely.
the so when the patterns are clear, then it doesn't really.
Then there is no issue.
Then by
No
and
issue.
large you'll be able to extract by and large.
Yes,
But you are right.
absolutely.
If the pattern is not clear, or if it's
Yeah,
completely, let's say, heavy tail distribution, right?
absolutely.
Then you are in
Right.
trouble. Yeah, I agree.
So,
Open area. So something that we are investigating with
sure.
our students. I believe our even PhD students are looking at that.
Okay.
Some of them.
Okay.
Okay, so let me go on.
Any
Any other quick questions? Yeah.
any other question? Most welcome, please.
Yeah, I mean, don't hesitate.
Okay.
Make it. If there any question you can ask me, don't worry about.
Okay.
Make
So
it
we
more
can go ahead.
interactive.
We can go ahead. I think, and then at
Okay,
the last.
fine. I'll probably give a lot of time at the end also.
Right.
Okay, let's go ahead. And in the interest of time, I'm going to probably run faster now. Okay, but I think the background being set, and that's why I thought I'll take good time in the background because now it'll be much easier for you to understand. Let's go to the problem number one that we have. Acknowledgement, our students in Delhi Technological University was so happy with these students. They slogged it out even though everybody was getting worried about the how will we have lab access, so on, so forth. But nevertheless, they really so it's a collaboration between DTU, IIT Delhi, UKIDAR, and the University of Cambridge that you can see on the right side. Okay, so the first work that I'm going to go deep into is to understand the performance of CNNs on resource-constrained edge environment. Okay, and we call it a latency memory optimized splitting. So the whole algo is called LMOS. Now, when you hear the word LMOS from now, don't be surprised. It's latency memory optimized system splitting. Okay. So splitting in latency memory optimized system, and that's what we call as LMOS. So let's quickly go to what we will look at. So we look at the problem formulation. But by the way, you now have a good background, and that's why I spent 30, 40 minutes there. So understanding results shouldn't take much time now. But it's important to know what results we are targeting and why they are important. We'll formulate the problem as an optimization problem. We look at LMOS, we look at the simulation results, we look at some results in a now. Please understand, we don't not only have simulation, we also have some very, very interesting results on a prototype, which is Raspberry Pi, and actually not only on Raspberry Pi, but also on actual mobile phones. Thanks to our smart students, they've actually been spending the entire. I think this group spent about months and months, 4 months, to figure out how will you run these algo, how will you run the CNN on an edge device like a mobile phone. Now you know the background, so I'm not going to repeat this at all. So as we all know, quick inference CNNs are resource-intensive networks. We know that by now. Deploying them on an edge device is problematic owing to memory computational limitations. Also, they're going to be consuming huge energy. So there are many approaches now that solve this problem. You could compress the model, you could do knowledge distillation, you could do network pruning. Okay, pruning. One of the examples is on your right. You remove some weights, right? So let's say some weights are really not relevant because they're very small weight or edges. I'm going to remove those edges. What will be the result? The result will be that I'm certainly going to do well in computational. I won't have to do much processing. It's going to come down. But the challenge with all these approaches is that I'm going to compromise on the accuracy of the model. Because the moment you remove weights, remove edges, remove certain layers, you will realize that you're going to compromise on the accuracy of the model. And all the computer scientists working on vision applications, and I'm sure many of you are working on vision. Rohit, even you are looking at vision. You cannot, nobody will accept dip in accuracy. That has to be extremely high, in spite of the fact that, there's a trade-off. So accuracy cannot be compromised. Okay. So what's the solution? So our solution was that can we explore splitting a convolution neural network between the edge and the cloud? So let's say there are n layers of a convolution neural network, whatever n be. The n can be 21, n can be 44, n can be whatever. We'll come to what that n is. Let's say n is 100, hypothetically, right? Can I split the CNN between, let's say, n1 layers at the edge and n2 layers at the cloud? Okay. So can I explore that splitting between edge and cloud, and then can I formulate that as a resource constraint optimization problem? Okay. And that problem will then minimize. So the two key constraints here, and observe this carefully. My objective is to split, I repeat, my objective is to split. So clearly, you'll have to appreciate that I can't be running the entire CNN on the edge. That's a degenerate problem, right? That's a dumb problem. I mean, I can run. So what are the extreme cases? Extreme cases are running the CNN entirely on the edge. Well, good luck, because then you are burning the edge, right? You're going to really kill the edge in terms of energy and processing power and memory consumption. Number two, what's the other extreme? Running the entire CNN on the cloud. Well, then they don't need the edge, right? It defeats the whole purpose, and then your latencies are going to kill you. So you really want to trade off. So keep something n1 here, keep n2 there. You want to minimize the overall system latency. We'll define what that is, and you want to maximize the resource utilization on the edge. We'll define what that is. I repeat, you want to minimize L and maximize resource U, which means you really want memory to be consumed. You don't want system to be unutilized, right? So that is the overall problem. And the way you solve that is tasks involved in solving the problem are you do a local computation of the convolutional neural network model on the edge. You send the intermediate results to the cloud server. Then you compute at the cloud, and then final results are sent from the cloud back to the edge. So there are 4 processes over here. And let me go back over here. If you give me a moment, please. Should have had that system over here. So you run. So let's take a better. Yeah, this is a better figure. So you run the CNN on you split the CNN. We'll figure out how do you split it, right? That's a research that we have worked on. So you split the CNN on the edge. You send the parameters to the cloud. The cloud does processing with the remaining layers, sends the results back to the edge. So really, it's a 4-way thing, right? 4 steps involved, which I highlighted over here in this slide. Okay. Now let's now look at some interesting results. First interesting important result. So we are plotting. Observe this plot very carefully. The plot one. So the entire our edge is, by the way, Raspberry Pi. Okay, as I said, this is all results on a prototype. Our edge is a Raspberry Pi. Server is a Ubuntu 20.04 system. We have assumed a bandwidth which is not very high. It's really 10 Mbps between edge and the cloud. Not bad at all, because I don't really want to send the entire CNN to the cloud. I only want to send a small component, right? One of the chunks of CNN to the cloud. So if you look at the first figure carefully, all the figures are plotting latency versus splitting point of the CNN for 4 different models: AlexNet, VG13, VG16, and VG19. Observation number 1, all these 4 CNNs have different layers, right? From 21 to 33 to 34, whatever, to 40 plus or whatever, right? I think AlexNet is 21 or whatever. So why 4 different CNNs? Because you want to. So observation number 1, very important lesson learned. You want to experiment with diverse CNN models. You don't want related models, diverse models with diverse layers. And then when you do that, plot the total latency and splitting point. Splitting point is the point at which you will split the CNN. Observation that you will see is that irrespective of, so the black line is the total latency, right? Obviously that is, so you will find that all the latency metrics, because I break the total into 4 parts, right? So there is a latency at the edge, which is called the computation edge. Then there is a latency from edge to server, which is blue color. Then there is server to edge, which is black color. And I'm completely ignoring the delays at the cloud because there are hardly any delays at the cloud. Cloud is like a whale, right? So that delay doesn't matter really, which we saw. So we really have three components. So the total is divided into three components. Sorry, four components. Computation at the edge, edge to server transmission, computation at the server is negligible, and server to edge transmission. You will find that the red line, which is the computational edge, is right below the total, which means the dominant latency. I repeat, the dominant latency, irrespective, yeah, at least in AlexNet and VG13, is because of the computation at the edge. Your neural network, the CNN, you split the CNN, and the computational power at the edge is a dominant, reason for that very high latency. Observation one. Observation two, you'll find that it's a sawtooth pattern, right? Latency really is a function of where you're splitting the CNN. Be careful when you split the CNN, because if you split the CNN at say very high layers, your latencies are going to go whopping, right. Vis-a-vis if you split the latency at lower layers, right. Please understand that higher layers mean you're sending a large chunk to the cloud, and lower layers mean you're sending a smaller chunk to the cloud. So clearly, the larger the chunk that you're sending to the cloud, the latencies are increasing, right? So it's an increasing function. uh, so observe that where you split your CNN is important for latency. You cannot say I'll randomly split it. No, it could kill your latency. So that's observation number one. Now what we did was with that result, and of course, I'll open to questions. I'll be opening up the floor to questions in a short while from now. But let me finish the whole concept. Then what we realized was that there are three latency components in this piece of work. There is the component of computation at the edge, which is on the left side. There is transmission from the edge to the cloud or the server, which is the middle component, and there is a computation at the server, right? X1 are the number of layers of the CNN at the edge. X2 are the number of layers of the CNN at the server, right? So recall, I'm splitting the CNN between X1 and X2, right? So the X edge is really the time taken to process the CNN with X1 layers, time taken to process CNN with X2 layers. C edge is the number of cores at the edge. S is the processing power. And so multiply the number of cores with the processing power, and this is nothing but the bandwidth. Okay, B is the bandwidth. Okay, so there are three components. The delays are split into three components: T edge, TTX, T server. And so the total latency is nothing but a sum of these delays, right? Total latency is really a sum of A, B, and C when the edge device computes X1 layers and the cloud compute X2 layers. And then you have a second objective function, which really is nothing but the X edge, right? That is, you really want the local computation at the edge device, right? Which computes X1 layers. So that's the second objective function, okay? And I'll tell you why you need that, because you really want to maximize the utilization at the edge. So we arrived at an optimization problem. Okay, I'll be happy to share the papers with all of you later on. If you send me an email. And then we saw that the problem could be, see, you want to minimize the delay, right? Obviously, look at this slide carefully. You want to minimize the delay, which is F1, and you want to maximize the resource utilization, which is F2, right? So you want to min F1 max F2. That's tantamount to minimizing F1 and minus F2. Okay, I think that should be fairly straightforward. So I have a function big F, which is nothing but F1 comma minus F2. I'm minimizing that subject to these constraints. Very simple constraint. I'm sure you'll appreciate this immediately. Constraint one is that my memory at the edge is obviously less than the maximum available memory, right? Obviously, my memory can't be. I can't have a memory consumption beyond the maximum memory at the edge. The layers have to add up to the total layers of the CNN. So whatever I split, X1 at the edge and X2 at the cloud, total sum is L, which is a fixed thing. and total CNN layers. And finally, x1 is less than equal to L greater than equal to 0, and x2 less than equal to L greater than equal to 0. So it's a multi-objective formulation and very interesting. We can now rewrite the objective function using a very interesting concept, right? Epsilon approximations, and arrive at a Pareto efficient solution. So for those who probably want a brief primer on Pareto optimization, remember that when you have multiple objectives, okay, just a very high level description, when you have multiple metrics, multiple objectives, and you want to optimize them, you land up to a large extent, working on arriving at a Pareto efficient solution. So you define a function in such a way that you can arrive at a Pareto optimal solution, and when you do that, this is what you get. I'll come to that. Okay, so this is the algorithm which results in a Pareto optimized solution, because these constraints are very different, right? Remember, you're minimizing the latency and you're maximizing the utilization, right? So LMOS again is latency memory optimized splitting, SS splitting. So I don't want to go through the algorithm, but let's look at the results. So let's look at the sensitivity of LMOS. Here are the default values in our that we leveraged. Okay, so we have a bandwidth which, as I mentioned, is 10 Mbps. We assume the number of cores, CPU speed, storage size, server cores are all mentioned over here. So you can look at that in the paper. That's not relevant for this talk. Let's look at the second set of results over here. So let's look at this very interesting set of results. So every time, I think we have to answer this question, how sensitive are my results to the various parameters? Yeah, that is very critical. And I keep telling the students, please do sensitivity analysis. If you don't do that, then I don't think you're going to make much headway, right? So here are the first results of the sensitivity analysis. See, this result told us that where you split the CNN is important. You can't randomly split. You have to intelligently split it. So it gives you some cues about splitting. Then you come to the other result over here, which now let's look at the plots carefully. So I'm plotting the fraction of layers at the edge. So the y-axis is a fraction of the layers at the edge, which is x1, right? And the x-axis is bandwidth, memory, edge cores, server cores. Let's look at the bandwidth and memory. Clearly, beyond a certain point, I will converge at the number of layers at the edge. And initially, they will increase. Initially, when the bandwidth is very low, I'll have very few layers, right? As the bandwidth is very low, I can only accommodate very few layers at the edge, right? As the bandwidth increases, that increases and saturates, and irrespective of how many CNN layers I have, from 10 layer to 220 layers, right? Let's see the memory. As I increase the memory, the gross memory of the edge, again, I find that the fraction of layers at the edge are increasing, right? I mean, they're very low at low memory. Naturally, this is obvious, right? When I have very low memory at the edge, I can't accommodate many layers, right? But as the memory increases, it grows. But interestingly, the takeaway from this slide is they converge, the curve becomes flat beyond a point, right? So no matter how much, so what is the takeaway from the A and B plots? No matter how much, there comes a time that your bandwidth will not affect your results. What's that bandwidth is what we are answering. There comes a time when any increment in memory will not affect your results. What's that memory is what we are investigating, right? So beyond which any increase will not benefit you at all. Let's go down. As the number of edge cores increase, of course, the fraction of layers at the edge will increase, obviously, but again, will saturate. Reverse will happen when you increase the server core. Server is the cloud, by the way. So as you add more and more cores at the cloud, you'll find that, well, the cloud has enough processing power and memory, right? So it can accommodate a large number of layers at the cloud, but therefore lower number of layers at the edge. So it's interesting to explore, see the sensitivity to all kinds of parameters in the splitting of CNN. Now, a very important slide on the top. Am I audible, all of you?
Yes, yes,
Yes, sir.
yeah.
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 So thanks. Yeah, just again doing a mic check. Very important graph plot on the top left, which is, well, I'm sure you would have asked the question, what is the accuracy? Irrespective of which model I'm using, whether it's AlexNet or VGGNet, which is 13, 16, 19, right? And I can even add more models over there. You will find that the accuracy is not affected by the splitting. Okay, it is not really affected. Of course, AlexNet gives a poorer accuracy, and the VGG 13, 16, 19 gives a much higher accuracy. Of course, that's because of the models, right? They are different models. But observe that the accuracy is not affected by splitting the CNN at the edge. So no matter where I split the CNN, there will be a very minor effect on the accuracy. That's a very important takeaway, because that's bound to be asked by uh, reviewers and researchers and many of you. Then look at the table on the top. Now, let's look at the table below. Let's start with the table number two. I'm changing the bandwidth and I'm seeing what are this. Here is the optimal layers, the layer at which I'll split, right? Clearly, you will find that as a bandwidth, this is the bandwidth between the edge and the cloud. As the bandwidth increases, obviously, I can have more and more layers at the edge, right? Obviously, I have more and more layers at the edge. That's clear. The trend is very clear, right? Similarly, as the storage is increasing, I can which storage? I mean storage at the edge, right? I can have more and more. I can accommodate more and more layers at the of the CNN at the edge. This is the X1 layer, right? Because X2 will go at the cloud. If you look at the bottom figures, you will find again I'm plotting latency and memory requirements, uh, and I'm right, for different models again. So I'm just showing the same thing in a bar chart kind of formulation, which is more appealing to the eye. But I think the takeaway from these slides is that one has to be studying not only the latency or the memory utilization at the edge, but also the accuracy. And you've got to do it every time you split the CNN. Let's compare our work. So clearly, I'm sure you would have asked your question of mind. Well, हमने काम तो कर लिया, but compare किससे कर रहे हैं, right? So we compare our work with three algorithms. So I'll come to what these are. DS is called deep split, and again, thanks to my student, I had a very sharp student in DTU a few years ago who's now in the US, and Rishabh Mehta. So Rishabh and I did some very interesting work on, and we arrived at one of the interesting basic papers in splitting the CNN at the edge. That was called deep split. What Rishabh did was, and Rishabh and I, we basically looked at only latency as a parameter. We didn't look at anything else, only latency. So deep split is only latency. Remember, LMOS is latency and memory, and you're optimizing it. I repeat, our proposed algo is latency and memory, and you're optimizing it thanks to the Parrot optimization, right? And you arrive at these layers, right, which are amazing. Distributed deep split is only when you look at latency. The result's not bad. LOA is ECO is edge computation only. So that's edge computation only. That's we call as ECO. Okay. So the four algorithms that you find are deep split latency optimized approach. That's LOA, and edge computation only. And look at the figure at the bottom. You'll find that, and then RS is a random splitting. Split anywhere at random, generate a random number and split. That doesn't help at all because that gives you very poor latency and very poor memory utilization. But you look at the LMOS, you'll find that. So just look at the LMOS on the figure below, the bottom plots. You'll find that no matter what the CNN model, LMOS is doing fairly well in latency. I mean, it's giving you pretty low latency, and I mean total latency. Remember, I mean total latency. Okay. If you look at the memory requirement, LMOS is again doing pretty well. It really doesn't consume much memory, right? Other than AlexNet. AlexNet is a big trouble monger. It does consume large memory, probably because of the features of AlexNet, right? But the question that we want to ask is how, if we compare our approach with other existing approaches, are we at least doing as well as the other approaches are? Answer is yes, we are. So the takeaway from this work, right? Yeah, again, finally, we look at the we also look at MobileNet V2 and SqueezeNet because they remember my statement earlier that when you compare CNN models, you must try to compare with a diverse model. In other words, ensure that the models are very heterogeneous. And we look at accuracy, latency, and memory use, and we find, and even with MobileNet V2 and SqueezeNet, you find that our LMOS, for example, with VGG19, which has a large number of layers, is doing pretty well. Very good in accuracy. Okay, very good in accuracy. Not bad in latency and pretty good in memory use also, right? Latency, we are slightly high than MobileNet and SqueezeNet, but that's also because the number of layers here are very small in MobileNet and SqueezeNet. So, Takeaway. What's the key takeaway? Splitting is a superior alternative for running CNNs at the edge. And so we conclude this direction of work, which is that if we run a CNN between an edge and the cloud, okay, it's like solving a resource constraint optimization problem at the edge. And that problem then minimize the latency and maximize the resource consumption. All experiments, both on Pi, SIFT, as well as Raspberry Pi, they do reveal that LMOS, which is latency memory optimized splitting, it ensures that different CNN models may be executed at the edge. It does, by and large, I won't say always, but by and large, it I outperforms the existing state of the art techniques. So I think the key thing is that you can split CNNs between the edge and the cloud, and you can do it without compromising accuracy. I think that's the important point, without compromising, by and large, compromising accuracy. What are the future directions? Well, you could certainly include energy, which we will in the next few slides. So my next work is with energy. You could split it in multi-edge cloud systems. You could do LMOS on smartphones, which is again my next paper work, the other set of work, and you could generalize LMOS for other architectures, right? For all kinds of other network architectures. Finally, you could explore reinforced neural networks, LSTM, scans, and so on and so forth. Now, let's pick up these two future directions and let's look at that work now. So that work is now, and not surprising, I'm sure it's not coming as a surprise to any of you. Let's now add the energy metric in our work. So the same framework, I'm now adding the energy metric. Okay. So now you call it latency, energy, memory optimization for CNN splitting or smartphone environment. Again, a wonderful collaboration between IIT Delhi and DTU students. I think they all collaborated so strongly and resulted again. This work is very challenging because how do you tap the energy from a smartphone? It's never been easy, and I'll tell you how we've done it. So this work now adds the energy component, and I'm not going to repeat all the background work, but now if you look at the approach, now you're looking at the mobile phones. So your edge is only the smartphones, number one. Number two, you are splitting the CNNs between the smartphone and the server, which is a cloud, by the way, right? So here is, if you look at the bottom right figure, you'll find that all kind of application, right? Imaging or video clips and all that, and your mobile devices are being used, smartphones are being used to extract certain features, whether it's classification, whether it's recognition, or so on and so forth. And you're using CNN, right? Additional metric is memory. And how do we solve the problem? Well, so we now formulate the same thing. We formulate a multi-objective problem that aims to minimize all the parameters to enhance the performance of the splitting algorithm. So so I repeat, the problem is now to split the CNN between the smartphone and the cloud. And again, like the previous work, it's identical to the previous work, except we have added the energy part. And it's very important to know that we have used the Android battery stats tool. So there is a tool, for those who may not know, there is an app called the Android battery stats tool. That tool has really come to a rescue big time. It is a very, very important tool for us. Because see, I'll give you an example. How do you measure energy? I mean, energy is a very broad word, right? You have to actually look at the energy expended for each and every operation in your smartphone, right? Transmission in Wi-Fi, reception, processing, right? Every operation of the smartphone, you have to quantify the energy expended. Thanks to the app, you can do that, right? So the 4 tasks involved in splitting a CNN on the smartphone are: number one, the local computation at the edge, which is the smartphone in this case. Transmission of the intermediate results to the cloud, which is step number 2. 3, computation at the cloud, which is 3. And finally, retrieving the final results from the cloud and sending it back to the edge. So the first set of results are again plotting the latency versus the splitting index of the CNN. Now remember, these results are for the smartphones. Now we are moving from an edge environment to even a more constrained environment, which is the smartphone environment. And we're running it again for AlexNet and 16, 11, and 13 VGG. You find that what is the observation from this set 1? You observe, number 1, that if red is the total latency, then green is the highest component of the latency. And what's green? Green is the upload latency, which means that, so very important observation, when you work on smartphones, the delays or the latency in uploading your partial CNN to the cloud can take a lot of latency, can eat up a lot of or they contribute to huge latency, right, as compared to the other aspects of the latency. Okay, so that's one of the important takeaways, because observe the green curve is very close to the total red curve, and green is the uploading latency, right? So that's the way. Is it surprising? No, it's not surprising, and we'll figure out why it's not surprising. Okay, it's because you really have a limited bandwidth between the mobile smartphones and the cloud, and you also are leveraging Wi-Fi network, which drains a lot of energy. This is over a Wi-Fi, which drains tremendous amount of energy, as we all know, but we could get that stats from the tool that we have. Let's look at the other results quickly. Now, we also have results for two smartphones. One is the Redmi Note 8, and the other is the Samsung J6. So we have results for both Samsung J6 and Redmi Note 8. You can see both are similar in terms of their behavior, which means where you split is important. So if you split somewhere at a random place, let's say if you split at, let's say, 4, then your energy consumed is going to be very high. If you split at, let's say, 14, the energy consumed is very small. So where you split is again very important. And again, if you break up the total energy into components like uploading energy, client energy, download energy, you'll find that the orange curve, which is client energy. So in this case, client energy is very crucial. Redmi Note 8, right? So in one case, the client energy is a dominant factor for the energy. In other case, it's the transmission between the edge and the cloud. And by the way, there is no one answer for all. It depends upon operating system, depends upon one smartphone to another, depends upon the CNN. So, but what's important in these results is a trend. What is a trend? Can you infer something which is a meaningful inference, right? Again, like last problem, we formulated a problem. Again, I'm sure you're not surprised because it's the same work as before. Although I must say it's a very complicated piece of work where we add the energy component. So now you have one latency objective function, right? And the latency is of three kinds: latency at the client, which is a smartphone, transmission delay from the smartphone to the cloud, and finally the latency at the cloud. That's the latency. And then you have the energy. And energy also has three components, right? The energy at the client, the energy to upload the CNN, the fraction of CNN from edge to the cloud, and there's finally energy to download, because the energy at the cloud really doesn't matter, right? So again, energy has three components, which we could quantify with appropriate constants. And finally, we have a third objective function, which is the memory at the client, just like the previous one. We want to ensure maximum utilization at the client. So you have three objective functions, and just like the previous work, and you have a proposed algorithm, you are doing a minimum of f1, comma f2, comma minus f3, and you arrive. So it's a similar thing. So you have a third, you have a third. So you're minimizing now the three f1, f2, f3 subject to the constraints over here. Obviously, you have to add a few more constraints because now there is also the energy, right? And the download and the time and download size. So I think these are fairly clear enough. If you read the paper, you'll have an idea of what these are. Very interesting results again. You will see, let's look at the table below. Smartphone. For smartphone, AlexNet, you split at layer 3, 11, VGG you split at 11, VGG 30 you split at 10. How did we arrive at these numbers in the table? The answer is, well, we ran the algorithm, right? The Pareto optimal algorithm. We applied the Topsis algorithm on that, and we finally arrived that if you really want an optimal, or I won't use the word optimal, almost optimal solution, uh, which means you want to minimize the latency and maximize the resource at the edge and minimize the total energy consumed, then you will split AlexNet at layer 3 at a smartphone. You split VG11 at layer 11, you split VG13 at layer 10, and finally you split VG16 at layer 10. So the numbers here are obtained as a result of the Pareto optimization that we have solved earlier, right? And we have corroborated that with our work on PySift. Okay, so very interesting results. We've again, like earlier work, compared this with other algorithms. I'm not going to go into all details because this will take so much time. We've compared the, this is called the smart, the our smart split algorithm with other standard algorithms. We have to compare them, otherwise you can't really convince that we are doing well. So we compare it with the latency based optimization, with energy based optimization, with CNN on smartphone, with CNN on cloud server, and with random splitting. And you find that our smart split is really doing pretty well, okay, in terms of latency. So smart split is doing pretty well uh, in terms of latency, right? In comparison to many others, EVO certainly. It's doing very well in terms of energy. Look at the energy plot. Smart split is doing extremely well, irrespective of which CNN it is, right? Energy is the lowest. I mean the total energy, right? And if you look at the memory utilization, again, smart split is really doing very well. I mean, it really doesn't eat up so much of memory at the edge device. In this case, a smartphone. Okay. So what's the conclusion then? Finally, the conclusion is that it turns out that the key takeaways from this work is that the upload energy is the primary factor affecting energy consumption. And so keep in mind that the network bandwidth is a very important parameter to consider. Smart split, which is the algorithm which includes energy, performs better than other splitting approaches. And it even optimizes a different objective function, including energy. Remember, now it's latency and memory utilization and energy. Okay. And we've again seen that the splitting between smartphone and cloud ensured high accuracy. I've not shown the results, but accuracy, yeah, there you are. Accuracy is pretty high, as is evident again from the work that I'll be happy to share with you. Accuracy is not compromised, unlike other compression based methods, which do compromise accuracy. How do you extend the work? Well, we can again extend it for other neural networks beyond CNNs. We could generalize work to diverse, to heterogeneous edge devices. Maybe you could have very, very different edge devices. Now the work will change. Please observe, because you're having a very diverse category of edge devices, right? So very interesting piece of work. Just to share with colleagues over here, we are now working on a journal publication, which will have a lot of our work, future work will appear in the journal publication, which we plan to submit to IEEE IoT Journal in just about a month from now. Telling our students that as soon as they have the journal paper, we'll be delighted to, they can be assured they'll go to the best university in the world uh, without any doubt. And I think that is exciting so many of them. With that, I'm coming to the final part of the work, some results in federated learning. Again, this is a work in progress. It is continuing, but some very interesting results on federated learning. Before I do that, let me ask a question to Dr. Rohit Kumar. Rohit,
Yeah.
I'm almost at the end of the talk.
Yeah, sure.
When do you think I should stop?
Oh, I think just you can quickly summarize the part that is pending from your side, and then for last 5 minutes we can have a question and answer session if you
Okay,
have.
so I'm going to just take another maybe 5, 7 minutes and we'll open
Yeah,
to
sure.
Q&A.
No, perfect, perfect. No problem. Perfect.
Okay, because this is an important part. The last part is also
Yeah,
important.
sure, sure, sure.
Okay,
Perfect.
so let me just come to that and just give me a moment, please. Where am I? Oops. Yeah, sorry. All right, so let's come to the last part of the presentation. Work. We have other works going on in progress. So let's look at what we have done again. I'm not going to. I think all of you now know what federated learning is, but just a quick recap. There are two parameters, C and A. Quick recap. So here is a central server which runs an aggregation algorithm. This is a very quick 1 minute recap. There are K edge nodes. They could be even mobile phones, no problem at all. The K edge nodes each has local data. I don't share the local data because of privacy concerns. I keep the local data. I only share the updates. I share the metadata, which for example is weights. I train it locally. I share the metadata. All of us do the same thing. All the edges do the same thing. They share the data to the centralized server, which aggregates the weights, churns it, processes it, and sends the revised, updated uh, model back to the edge nodes. So this keeps on iterating till you converge. When do you converge? Well, maybe till you arrive at certain accuracy. So that's when you converge, right? Obviously, you've defined certain measure, certain accuracy threshold when you converge. So that's the background. You have two important metrics over here. One is the model accuracy, which is A, and other is a C, which is the time it takes for the learning model to converge. So throughout, we'll be using C and A as two key metrics in federated learning, which we are going to optimize. What do we vary? We'll vary the number of edge nodes. We'll vary the strategy to select the number of optimal worker nodes. Well, we call the edge nodes as worker nodes because they really are going to process the data, right? So we call them worker nodes. We will see what happens when nodes fail, and finally we'll look at a fault mitigation strategy. So again, a fairly intense paper, which is now going to be, this is with the students in IIT Delhi, and I believe even some D2 students may start working on this and extend the work in this paper. Okay, so let's look at the first set of results. Very interesting results. I'm going to go straight to. So the first, yeah, I'm going to go straight to the results. So the first result is the result when you change the number of edge devices. So what happens when you increase the number of edge devices, and what happens to the convergence time? Okay, let's look at that. So I'm going to figure out what's the worker count impact on the federated learning model, and then we'll find out what is the optimal worker percentage for the federated learning model, and what's the optimal worker set selection strategy. Okay, so K is a set of all workers, C is convergence time, A is accuracy. I repeat, K is all the total number of worker nodes, which is edge nodes. C is convergence time, A is accuracy. Okay, let's look at the first result. Very interesting result. All right, so let's look at the results over here. The first result is very interesting. If you look at AlexNet and ResNet particularly, you'll find that as you increase the number of worker nodes, but remember, worker nodes are nothing but active edge nodes. I repeat, they're edge nodes. Okay, they're participating in this training. So they're active edge nodes. And we're plotting this vis-a-vis convergence time. You find that there is a number of node n star at which the convergence time is the minimal, beyond which it is not going to help you if you have larger and larger of nodes just because you want to distribute a machine learning algorithm, right? So there is an optimal minima before which the convergence time increases and after which it will increase, like a convex function. It's not convex, it's a convex-like function. Similarly, for ResNet, you will find that, just give me a moment, please. Hello? Yes, hello? I'm in a call, please. Can I call you back? I'm in a call. Thank you. Yeah. Right. So sorry, that was an important call. So apologize, but it was an important call from the government ministry. So if you look at the AlexNet and ResNet, you'll find that it's kind of convex-like functions, which is very interesting. On the other hand, if you look at LeNet, the other CNN, right, totally different, totally different architecture. There you find the reverse is happening. That there is that beyond this, let's say 400 nodes. 400 nodes is a wrong set of nodes. It'll give you the worst convergence time. But anything before that is fine. Anything after that is fine. So again, what is happening is that these results are helping you to figure out what is the optimal number of worker nodes that give the lowest convergence time. Let's go ahead. Okay. So the key takeaway is that we can find the optimal, number of nodes based upon which will impact the convergence time. Let's look at the other quick plots in the next few minutes. Right? Let's look at the accuracy. As you increase the number of worker nodes, as you increase a fraction of worker node, by the way, worker node is nothing but edge node, right? So as you increase that edge nodes, you find that the accuracy is increasing. Not surprising, right? Not surprising at all, because you have more and more data split across, distributed nicely across the worker nodes. But there comes a point where the accuracy becomes flat, and that point is roughly 0.7, right? 70%. So that tells us that look for this data set that we've got from wherever, which you will see in the work. 70% is a good number of worker node optimality, good number of optimal worker nodes, which will yield me a fairly high accuracy. Because beyond that is an overkill. I won't really change my accuracy. And my convergence time is also not bad at all, because for 70 worker nodes, 70% of the worker nodes, convergence time is not bad at all. Okay, because beyond that it will increase significantly. So it just, the two curves help us to tell you the optimal worker percentage for federated learning. And of course, this depends upon the data distribution. And finally, we arrived at an optimal worker set selection. How would you, with the diversity that you have, with all the diversity that you have, heterogeneity that you have, how do you choose the worker nodes? And the answer was, well, one of the answers was in the equation that we developed, which was a selection score. So that was a function of the transmission time D, of the volume V, and so volume V, computation power P, and the network bandwidth B, and then kappa and alpha were constants, right? So we arrived at a selection score. So the higher the score, the better for us. And so each node will have a selection score. And if the score is high, then that node will be a candidate that we will select for the federated learning algorithm. Okay. And you can see now that now, this is very interesting, this plot, right? Almost my last few results in this talk, that if you look at our S-based strategy, which is the lowest, right, which is the orange curve, the test loss is the lowest. My loss is the lowest for the S-based strategy, which has a selection score, right? In comparison to a strategy which is random, which is the worst, or only that only takes care of bandwidth, or that only takes care of volume or computational power. So if you combine all these three intelligently, then your results are going to be very, very interesting. Okay. And finally, what happens when nodes start failing, and we realize that, well, we need a federated learning approach when nodes fail, and a fault mitigation approach. And we ran an proposed an algorithm, and very interesting results that as the nodes fail, uh, so so we've compared our federated learning proposed algorithm, which is called FedFM, with the well-known Fed average, and we see that FedFM does very well. The left side is when 20% worker nodes fail. The right plot is when 40% worker nodes fail, and we also have a plot when 60% worker nodes fail. You find that irrespective of how many worker nodes fail, whether it's 20% or 40% or 60%, you'll find that the Fed FM, which is our proposed algorithm, okay, the accuracy is strictly higher than the Fed average, which is, by the way, very well-known algorithm. Fed average, if you all know, many of you may know, Fed average takes an average across all the nodes of the edge devices, right? So we are doing pretty well. Uh, Now, how are we extending the work? Well, we are now trying to answer. We try to answer specific questions based upon the application. So for autonomous vehicles, you'll have one application. Other application may be healthcare. Third, maybe, let's say, you know, uh, planning for a smart city, right? So there are all kind of apps. We're going to pick up an app and see how will that. So basically, we're looking at the sensitivity of all the results to applications, to changing applications. Number one. Number two, we're looking at new topologies. Observe that this was completely, the entire work assumed a star topology, right? If you look at our topology, this was topology, right? That all the nodes are talking to the centralized server. Why should this be a star topology? It could be mesh, it could be torus, it could be any other topology, right? So can we repeat the results with the different topologies, right? And finally, and the most important extension which we're doing now as I talk to you, and that's going to be a very important extension. What happens when you have different data distributions? How do you handle scenarios when each edge node has a different data distribution, has an imbalance, and then how do you maintain fairness in such a solution? This is a very, very important topic, which is also called statistical aspects of federated learning. Okay. My last few slides, and I'm going to wind up my talk. So where are we now? Well, there are numerous research problems in the intersection of AI, ML, and systems. Please understand that the problem can be dissected into two parts. One is systems for AI, ML, right? Which means you could have your own, chipset, or a processor, or a new environment for AI/ML. Another is AI/ML applied to systems, which we are talking about, right? So remember, the two components of AI/ML and systems. It's clear that edge computing systems are becoming crucial for real-time or semi-real-time applications. Edge computing system may not be the best for applications that are not real time, but for real time applications that require very quick results, like autonomous driving or vehicular communications, right? Or any real time, let's say industrial IoT, I really need edge systems. And now I want to leverage AI/ML on edge systems or edge nodes because I really want to make intelligent decision. And as I think even Dr. Rohit Kumar pointed out, I really want real-time answers uh, to what happens with diverse traffic running on the edge, and can that help my business, and can that help me come out with some fundamental publications, right? So it seems to me that AI/ML will continue to play a key role at the edge node going forward. Many research problems in the area. You actually seen a plethora of problems in the last 2 hours, right? From deep learning to federated learning. Please understand the problems is extremely complex because it's a distributed setting. These are lossy environments. There are wireless links all over. Therefore, you can play with the channel model, loss model. It's a distributed network. You can. What happens when links are disconnected? What happens when nodes are, when they fall, right? Or when nodes are disconnected or nodes go down. Finally, privacy and security are very critical areas going forward. What happens when nodes fail? What happens when there's a DOS attack? Are there any answers? Will federated learning work? Will deep learning work? I don't know, but it seems to me that it's definitely a very exciting area of research. And a few of our students are actually working on that area uh, as we talk. Finally, I think many of you will probably explore new attack vectors because this is a new area, and there could be attacks at every level. There could be attacks at which are not seen earlier in IoT or cloud. And I think it's a good time to propose those attack vectors. I think my final comment to all, my 2 cents of advice to all my colleagues, and I know many of you are doing some wonderful work, all of you are doing wonderful work. But the lesson that I learned from the last few years is that, particularly last 4 5 years of working in IoT and now edge and cloud, is that prototyping is very critical. Because remember, you have Python, you have PySift, you have PyTorch, you have all kinds of PyStars with you, right? But will that help in getting a good paper? May not. You may get a workshop paper, which is again good. I'm not denying, I'm not underestimating. I'm just saying that you need to protect your work, and it will only happen. You'll only get appreciation when you have a prototype or a POC to showcase, a real life POC. Because without that, it may be very hard to publish papers in even some very good conferences. Finally, great time to explore startups in the area. I think this is a wonderful time. Of course, one needs funding, and that always is a challenge. But assuming one has a funding, it's a great time to explore the area. And I think one lesson I've learned right from my career, right from the time I started working in IBM days, or even my Sasken days when I used to work in Nortel in US, was that collaboration is the key. We have to collaborate. I mean, look at our example, right? I not only work with IIT Delhi, but I work with DTU and with multiple industries and other ISC Bangalore and many other universities. And I think that's one lesson I want to share with our colleagues in DTU, that you will probably make a huge impact as you increase your collaboration, not only within DTU, but even outside your place, because that is going to get you different ideas, different mindset. And I think that convergence will may take time, but it's going to be a very nice convergence. Okay, I'm going to stop here. I know I can go on and on and on, but I just hope that I shared with you some very important areas of research, and they're very current. I'm sure I can give a tutorial in these areas, and probably will going forward. But if but if I could succeed in highlighting some open research problems, and many of them, then I think I would have succeeded. So thanks, and I'll be very happy to take any questions.
Dr. Shorey, I have just two pieces of small questions. That
Sure.
right now you were talking about the number of edge nodes, right?
Yeah.
So you had simulated with several number of nodes. My question is that, do you assume that this number of edge nodes are already known in advance? You are aware of this number of nodes?
Number of edges. So what happens is that no, you don't. You look. So it's a good question. See, it's a
Why
trade-off.
I'm asking, just I will add to this, because why I'm
Yeah.
asking this question, because I don't think that is it practically possible that we will already be aware in advance about the number of edge nodes. And
Right.
if we are not aware, then should we not use some RL techniques to estimate that number of nodes, and based upon that we should do the next part?
You could, so there are two points over here that I want to highlight. One is that you will have to experiment. See, based upon the app, you're going to figure out what is the optimal number of edge nodes. There's no clear-cut answer. It's clear. See, if you recall our results, you saw that if you have very large number of edge nodes, it doesn't help you, right? It's actually detrimental, and it's going to increase your cost significantly. So it doesn't help you at all. So we saw that since you want to minimize your complexity and the cost, you really want an optimal number of edge nodes, right?
Absolutely.
You don't want very small number because it won't help, right? ML, if you distribute it with very small edge nodes, it really won't give you much high accuracy. So there is just that optimal number, call it N star, where you will have high accuracy, low latency, and that is completely a function of the application. And it changes from one application to another.
Right.
So really no mantra to figure out what's the optimal number. It's really a function.
Okay.
But I think an important question that Rohit, you pointed, a very interesting question is, if we can find out the sensitivity of the optimal number of nodes to the application, even they could be broad applications, right? That will be a very, very important result.
Right.
That's an ongoing work. So broad could be, automotive, autonomous driving is one family, other families, industrial IoT. So if we can figure out कि हम एक ऐप से दूसरे ऐप जा रहे हैं और the optimality is changing significantly, that's a great contribution. We don't know the answer.
Right. Okay, guys. So any question from participants will be most welcomed, and thereafter we will wind up this. So any question from the participants? I know that it's already lunchtime for everyone, so maybe they are hungry. So anyway,
I hope it was clear to most of our colleagues. I mean, I hope it was clear. My speed was okay and all that.
Absolutely. So maybe in future as well, so you can just refer to the website of sir, and in future also, if you have any query related to his talk, so just you may write him down, and then obviously he replies very frequently, right? So
yeah, you can always send me an email anytime. I'll be happy to answer questions. And I said UKIDAR also has, as I mentioned, we have a large number of PhD students. Anyone who's exploring, including your students, by the way, MTech students or even some faculty exploring joint PhD, which is very cutting edge. I'll be happy to help you in any way I can. That's another avenue we could look at.
Absolutely. Right. So if we don't have any questions, then we would like to bind up the session by saying thank you so much, sir, for just spending your time with us and giving a very detailed idea about all the work that you are doing, and obviously other parts also like collaborations and for other things which you have motivated. So hope so that participants have been got a good advantage from here, and it is going to be helpful in the future as well, right? So I will say thank you so much once again, and hope that we will continue success in future as well.
Thanks so much, Dr. Rohit Kumar. Pleasure interacting with all of you. And as I said, please I'll be happy to, if you send me feel free to send me an email with questions that you have. You have my email ID. You can do Google search. I'll be happy.
By the way, I'm going to meet you personally in a few days only in Cognizant, right? So
you're coming. Excellent.
Yes, excellent. I'm coming there, so I will meet you for sure. Right?
Very good. So we can brainstorm with you, because I can share with you what else we are doing.
Yes, absolutely. I will.
Very good.
Sure, right?
Excellent. Yeah, I look forward then.
Sure. I will be there. Right. Okay.
Thank you
so much.
Yeah,
thank you. Okay.
Thanks for the invitation. Signing off. Thank you. Bye.
Okay. Thank you.